So I came to calculate the rolling resistance force as 220 Newton. I'm assuming that the rolling resistance coefficient remains this value. Now how do we actually determine that? Well, in order to do that, we have to be dependent on the actual experiments. So the experimental values will be best suited for here to enter in this calculator. Now for air drag calculation, I am entering the height and width of the vehicle and calculating the frontal area, which is basically the multiplication of these two, and I'm assuming the drag coefficient is 0.308, and I'm assuming the highest speed. So the top speed of the vehicle is 145 kilometers per hour, and keeping all units same, the air drag force comes out to be 880 newtons approximately. Now if I do this rolling resistance and air drag only, basically this is the case where the vehicle is running at a constant speed. So there is no uphill and there is no acceleration. There will be only two forces applicable on the vehicle, and that calculation where you have 220 newtons along with 880 multiplied with the velocity, which is equivalent to 145 kilometers per hour, it will be converted into meter per second, and that comes out to be 44 kilowatts. So the 44 kilowatts is the power required by the vehicle in order to run at a constant speed with this assumptions, where the drag coefficient and the rolling resistance coefficients are very important values. So this is the calculation for these two forces. Now why I have separated this? Because normally the uphill cannot be the case every time, the acceleration cannot be the case every time. So the forces acting on the vehicle, they will not be acting all simultaneously. They may be present or they may not be. So let's assume the hill climbing angle is 10 degrees, which is usually the case with a flyover, and the speed at which the vehicle is running on the flyover, that I am assuming is at 80 kilometers per hour. So if this speed is 80, then we need hill climbing power itself to be 76 kilowatt. So this is the value of the hill climbing power required, and if I assume that my vehicle should run on the flyover at 100 kilometers per hour, basically it will end up having 95 kilowatts of power. So basically this is mechanical power required on the wheels, and if you assume the efficiency of the gearbox, if you assume the efficiency of the motor, the sizing of the motor has to be much higher than this. So these are the forces acting on the vehicle and added one after another over here. Now for your reference, I have added another vehicle as well. So if you consider a lighter vehicle with the similar values basically, and if you have a low speed electric car, let's say your top speed is 100 kilometers per hour only, then your vehicle will require only 12 kilowatt power to run at 100 kilometers per hour speed, and in order to do the hill climbing it will require 45 kilowatts. So the sizing of the motor or power estimation of the motor will be somewhat less if you have the less weight of the car, and therefore people are talking about the light weighting and the new mechanical design for electric vehicles. So let's go to the acceleration as well, and acceleration calculation is done with an assumption that what is the rate of acceleration you want. So here for a Chevrolet Bolt EV, the acceleration is from 0 to 96 kilometers per hour. It should happen in 7 seconds, right? So imagine the situation where 0 to 100 kilometers per hour is below 7 seconds. The amount of power required for this acceleration alone is 123 kilowatt. So keeping all these values in mind and all this basic mathematics, we can assume that the power estimation for this type of the vehicle is equivalent to 150 kilowatt. So 150 kilowatt may be the continuous rating of this motor used in Chevrolet Bolt EV, but the peak power rating and the peak torque demand can be different. So let us pay attention to the torque values as well. How do we calculate the torque from the force? Well, it's basically very simple. You need to find out the radius of the wheel and convert the all force values into Newton into meter. So basically the torque represented as Newton into meter. Newtons we already have calculated for this 4 categories, and if you multiply with the radius, you can easily calculate the Newton meter torque available on the wheels. So let's do this for the Chevrolet Bolt. So the Chevrolet Bolt has this type of tire, and it has 0.3 meter radius considering the thickness of the tire as well, and 8,840 newtons is the addition of 3 forces acting over here. I'm considering the 3 forces, not all 4 forces simultaneously, and the Newton meter which is available on the wheels, which comes out to be 2,850 Newton meters on wheels. If we assume that the force is this much and the radius is this, and if I consider the gearbox, so basically the gearbox is a reduction speed gearbox where the speed will be reduced, the torque will increase, right? So the torque on the wheels will be much higher than the torque available on the motor shaft, right? So therefore I am considering the final drive gear ratio which is available from this specification as 7:1, and if I do this 2850 divided by 7, which comes out to be 407 Newton meter, and which is approximately the torque which is developed by the motor, which is 360 Newton meter. So these are some of the basic calculations for a vehicle which has all these forces acting around. Now it's the time to get back to the presentation and imagine how this much power can be put inside a motor, and that's where we start with the motor design. So if you remember, we discussed about the forces acting on the vehicle, which are fundamentally the forces required for running the vehicle and which are at typical velocity, right? So what is the meaning of a drive cycle and why we are interested in learning about drive cycle? So fundamentally the drive cycle is something which is going to give us idea about the vehicle speed. So we have calculated power P in kilowatts for running the vehicle at given velocity, right? So we have calculated a single point calculation, but the velocity of the vehicle never remains same, right? If you consider your urban driving or maybe highway driving, you never drive your vehicle at exactly constant speed throughout your ride, right? So that's why, which is very important to consider the pattern of driving, right? So the pattern of driving is basically known as driving cycle. So driving cycle is defined as variation in speed with reference to time. So the constant velocity computation will give us instantaneous power, but if we are interested in overall power or average power or calculating energy from this, we need to pay attention to the pattern of driving. So in order to calculate this, we need to understand what is the driving cycle. I'm going to quickly explain you. Basically, the driving cycle concept was mainly developed for testing the emissions, but now it is also very widely applied for the vehicle testing. So one example is Federal Urban Driving Schedule. So what is this? So here is a graph of Federal Urban Driving Schedule. So this is the data available where you have approximately 1400 seconds on the x-axis and the y-axis is speed in kilometers per hour. So this is how you are running your vehicle if you follow the FUDS. So this is one such standard drive cycle available for test purpose of the vehicle, but you never know what is going to be your drive pattern, and therefore this is going to be the very important point for electric vehicle motor selection, where you need to know what is going to be the peak case and how much is going to be the average velocity, right? So if you consider purpose of the vehicle, if the vehicle purpose is going to be the highway, then you need to assume the average velocity is going to be very high. If you consider the vehicle purpose as urban driving, driving in a city or in a traffic area, which is average velocity which will be much less. So these are some of the important points for a drive cycle. Let's move on and discuss about classification of electric vehicle motors. So this classification is based on this reference book, and basically this classification is according to the construction, and there can be another classification according to the type of the flux or maybe type of the supply and so on, right? But here is a main classification related to whether the machine has commutator or not. So basically the commutator function is going to change the type of excitation in the winding from alternating to direct. So if the commutator is present, basically it's a DC type machine, and the DC type machine can be either series shunt separately excited under the wound field category, or it can be permanent magnet DC machine. So this is also one such highlighted category which is popular for electric vehicle motors. If you consider the commutator less machine, basically the question arises, how does the commutation happens then? Yes, the commutation happens, but it is electronic commutation. So for electronic commutation, you have the fundamental requirement of power drive, or basically we call it as a motor drive or inverter in case of a DC supply for a motor. So the commutation basically happens electronically, or if it is the case of a DC motor, or if it is a case of an induction motor, it is not required, right? So the commutation is not required because of the working principle of the motor, right? So let's see the first category, which is the induction machine, and there are two categories. Usually the wound rotor motors are not preferred for EV. The squirrel cage induction motors are preferred. In case of synchronous, there can be three different categories: wound rotor, PM rotor, and reluctance rotor. So this PM rotor type of synchronous machine is very popular for electric vehicle application, and this it can be again classified into two more categories: permanent magnet brushless AC machine and permanent magnet brushless DC machine. Normally it is called as BLDC motor, and this is called as permanent magnet synchronous motor. So again, another classification is doubly salient, where the saliency is present on both stator and rotor. The meaning of the saliency is the poles are projected outside. So the switch reluctance motor is also popular, and the permanent magnet doubly salient motors are also popular for EV applications. So where the stator is going to have rotor. So whether the stator is permanent magnet or rotor is permanent magnet, there can be another classification. Now this can be again classified into flux reversal or flux switching or doubly salient permanent magnet, and this three classification can be again having an option of controllable flux. So flux controllable DSPM, flux controllable flux reversal PM is another category, and this can be the last category. So the doubly salient motor is another classification of electric vehicle motors. Vernier motor is basically going to offer the high torque at low speed, and basically it is also known as the magnetic gearing motors. So the magnetic gearing motor is called Vernier motor from the Vernier effect. So the Vernier permanent magnet motor is also one of the popular machine for electric vehicles. So this is the overall classification of electric vehicle. Now there can be n number of different ways to classify the motors, which can be based on the type of the flux. It can be radial flux, axial flux, or linear flux, and there may be another classification tree. So this is about the classification of EV motors. Now let's learn what are the factors affecting the choice of EV motor. So as we have seen, there are many different types of motor. Which one is going to be the best choice, right? So how do we decide on the type of the motor, power rating of the motor, and configuration of the electrical machine used for propulsion? So there are many factors actually affecting this choice. I have shortlisted here few important governing factors. So here let us talk first about speed and torque requirements. So the very first thing is speed and torque requirement. So what are the speed and torque requirements? So as we have calculated in an Excel calculator in our previous video, you need to understand how much is the speed required on the wheels, how much is the torque required on the wheels, and those speed and torque can be translated through the gearbox, and you can actually take into account the gearing ratio, and you can calculate the speed required for motor and torque required for the motor. So this values can be actually taken as a maximum value for the motor consideration initially. So let's say the highest speed required by the motor in order to run the vehicle at a highest speed, let's say the top speed is 100 kilometers per hour. So for 100 kilometers per hour linear speed of the vehicle, how much will be the angular velocity of the wheel and how much should be the speed of a motor, how much RPM should the motor have, that can be calculated easily, and that will be the deciding factor of the highest speed. Similarly, when your vehicle is going to start with the maximum acceleration, it is required to produce maximum value of the torque, and therefore this torque should be considered as the maximum possible torque produced by the motor, and it can be produced at a very low speed. So at a very low speed, the machine is required to produce the high torque for acceleration. So once this factor we have considered, the second factor is actually related to speed and torque, and that is very important factor known as efficiency. So what is going to be the efficiency of the motor at given torque and speed? So you have calculated maximum speed, you have calculated the maximum torque, but what about the efficiency at all speed and torque? So this is very important parameter to be considered. Why efficiency is very much important? We have already seen this in case of why the battery systems are high voltage, right? And we know that in order to reduce the losses happening because of I²R, we usually choose the high voltage system. But let us talk about efficiency for a motor. Now let's say the motor is having 80% efficiency and all other stages are also similar to 80% efficiency. Then the overall efficiency will be less than 50%, right? Because there are 4 to 5 different stages connected back to back, so the cascaded efficiency at all stages, right, the overall efficiency of the vehicle will be very low. Actually, the overall efficiency depends on the lowest efficiency of each component coming into picture. So the motor efficiency is very important parameter, and because here the motor operates at very different operating points, and therefore it is very important to design and develop the motor according to the efficiency. The third factor is cost and availability of the material. So if you are choosing the permanent magnet material, and if you are choosing let's say some type of copper for winding, right, you need to take into consideration that how much is going to be the availability of the permanent magnet material and what will be the cost, and it may require to be evaluated for the lifetime of the motor, right? So you may think of a motor undergoes a maintenance, right, after let's say some amount of time. Now how much is going to be the cost for repair or replacement of any of the component? So that has to be taken into account, and considering that there is a lot of research going on with the permanent magnet materials for the EV motors, as well as how this cost can be affected in the future. So the permanent magnet material cost is going to be, let's say, volatile. It is not going to be fixed. It depends upon the demand and the supply. So if the supply is going to be less and the demand is high, the cost will definitely rise. So the cost and availability is going to be the deciding factor for the choice of EV motor, because once you design a motor, that design will go into manufacturing, and at least for 5 to 10 years of duration, that particular motor will be in operation and in repair and maintenance. So you need to be sure that for that much duration of time the similar type of material will be available, which is decided at the time of design. So this is another important factor. Now the last factor I want to discuss about is the thermal performance and the reliability. So here the thermal performance is basically how much is the volume allowed for the motor, and there are actually two things we need to consider here. One is a continuous duty and one is a peak duty, or we can say the maximum value of the power which motor can provide for shorter period of time. So usually the motors are rated, the normal motors are rated from S1 to S7 class of duty. So this S1 to S7 class of duty are actually decided based on their operating conditions, right? So for example, there is one motor in the textile industry and which is required to be operated during let's say 12 hours in a day. So 12 hours in a day. Now how that motor will be operated in 12 hours? For that 12 hours the motor may operate at a continuous speed, or the motor may operate like forward, stop, reverse, again forward, stop, reverse. It may be operated like that. It may be operated like forward, brake, stop, reverse, brake, stop, right? So there may be different operating conditions and duration of a typical motor. What about EV application? EV application actually undergoes different condition according to the drive cycle. So based on the drive cycle, the motor is required to produce the power, and because the drive cycle speed is continuously varying, you never know how you will drive your vehicle, right? It depends on many conditions. It depends on the traffic, it depends on environmental condition, and so on. So how you are going to drive your vehicle is going to be affecting the overall thermal performance, right? So the thermal performance may actually affect the life of the permanent magnets, right? So therefore there is a trade-off between non-permanent magnet motors and permanent magnet motors for electric vehicle applications. So some manufacturers are trying to use induction motors and switch reluctance motor, which are non-permanent magnet motor, and many manufacturers, due to advantage of permanent magnet material and their advantages compared to their disadvantages and the cost, they are using permanent magnet materials type of motors. So the thermal performance is again the key aspect where you need to decide on how much will be the overall lifespan and how much will be the life affected due to the every temperature rise. So in order to understand the second point, let us try to have a graph of speed, torque and efficiency from a manufacturer. So we can consider a graph of speed versus torque characteristics of a motor, where we are going to discuss this factor efficiency along with torque speed, and we will also discuss about the type of duty of the machine and its thermal effect. So let me show you this graph. You can see this is a typical graph of speed versus torque. So on the y-axis you have torque in Newton meter, on the x-axis you have speed in RPM. So the highest RPM for this particular motor is 7500, and for 7500 the machine is going to produce a relatively lower value of the torque, which you can see from here. Now this machine can actually produce a very high starting torque such as 150 Newton meter at very low speed regions over here. Now what you see inside this, right, are the actually efficiency contours. What is the meaning of a contour? Contour means the value of the efficiency for given speed and torque. So for example, if I take the RPM which is let's say equal to 1000 RPM and the torque value which is equal to 90 Newton meter torque, and that point will be lying somewhere over here, and that point is having the efficiency of 90% because it is lying on the efficiency contour plot of 90%. So all this points are actually having 90% efficiency. So this particular graph is actually derived from an experimental data of a motor, or it can be derived from the software tools such as Ansys. So here you can see the efficiency plot will be very useful if you are interested in evaluating the overall efficiency of your entire vehicle, and you may be interested in knowing more about how will be the efficiency point at a different period of a drive cycle. So let me make it clear to you with a few more edit in the diagram. So okay, let me erase all the things. Okay, so here when you talk about a drive cycle, so let us assume that our drive cycle, which is speed versus time, is something of this nature. So here we have this as a nature of speed versus time, and this is how we are running our vehicle. Now for all those speed values, we might have the points in the graph which will be something located over here. So some points during acceleration can be located over here at probably this duration of time. Something where we have the peak speed, those points can be located over here where the torque requirement is not much but the speed is very high, and something, these points may be located over here in the speed torque graph. So you need to consider having all these things together, and you need to understand how all these points will be located inside this and where your maximum points are located. So you need to assume whether your maximum number of points are located in this region, or maximum number of points are located in this region, or maximum number of points are located somewhere over here. So if your points are located in this third case which I have highlighted here, your efficiency is going to be best because it is 90 to 92% efficiency. So you need to understand how your motor is going to be utilized in this case. So once you have understood this, I think you know now better about the choice of EV motor and how the efficiency is important apart from speed and torque. And as you can see, if the motor is operated at very high speed, the efficiency is very low, such as here. If the motor is operated at very high torque and low speed, the efficiency is very low. So the efficiency actually decreases as you move away from these points where this is the highest efficiency contour, where it may be 94% efficiency for this case. And the other important thing to understand is the plot which is going to be related to the type of duty. So what is that plot? You can see these two plots over here where you have 30 kilowatt motor power rating, which is this plot, and you have another plot which is 50 kilowatt intermittent operation. What is the meaning of intermittent? It is a short duration period, right? So for short duration period, you can actually get higher value of torque and you can actually get more power from the motor for short duration of time. But during this period, the motor may produce higher amount of heat, and you need to know that what is going to be the continuous power rating of the motor and what is going to be the peak power rating of the motor, and you need to understand from manufacturer's data sheet that how much is that duration. So for how much duration I can get 50 kilowatt from a 30 kilowatt continuous motor, and whether the duration is in seconds, few minutes, or for how much, and whether do we need to provide more cooling during that operation or not. So with this, I hope you are now clear about which are the factors affecting the choice of an EV motor. In the next video, we are going to learn more with Ansys tools that how we can start the initial efforts in the EV motor design. So in the next video, we'll be looking at Ansys RM Expert, and we'll talk about the template based design for electric vehicle motors. Thank you for watching this video.